Now I would like to welcome our speaker, Margaux. Welcome, and thank you for joining us today. Quick intro. Margaux Masson-Forsythe is passionate about applying technology to make a positive impact. As the director of machine learning at Surgical Data Science Collective, her work involves leading research focused on utilizing video data from surgeries to develop tools to provide surgeons with relevant feedback and insights on their performance. And some of her past projects include developing spatially explicit models for risk assessment, computer vision models for automatic tree measurement, and generative adversarial network for visual simulation of reforestation. Her professional interests involve deep learning, computer vision, software engineering, product development, image processing, science writing, and advocacy for diversity in STEM. In her free time, she likes to hike, climb, travel, work on photography or short movie projects, and spend time with her family and friends. Um, Thank you for joining us, Margaux. And I will pass it over to you.
Great. Thank you, Sumya. I will start sharing my screen. Okay, is it all good? You can see my screen?
Yep.
Perfect. Great. Well, hi, everyone. I'm really excited to give this introduction to computer vision today. I love computer vision, and this has been my career for the past several years now, so I'm excited to share about it. And this is part one. Part two is next Tuesday. So the part one is more introduction, and next week I'm planning on doing some more deep dive in implementation of computer vision, and I will have some live coding notebook, etc., with Python code so that you can really get understanding of how it works. Okay, so first of all, what is computer vision? So computer vision is a subfield of computer science and artificial intelligence that focuses on extracting, analyzing, and understanding visual content. So for example, you're gonna see a lot of pictures of my dog in the slides, but this is my dog Piper, and I always use him for a lot of demonstrations. So some example of computer vision tasks are classification, classification localization, object detection, instance segmentation, and semantic segmentation. And I'm going to go through every one of these tasks and explain what they are and how they are used. So first, classification. So classification is, oops. Well, we're gonna see an example here. Let's classify these images. So the first one is dog. We have an image of dogs. Then here we have an image of cat, and here we have an image of clownfish. So it's pretty straightforward. What is it? So how it works is that you have the image that is passed into a classification computer vision model, and the model will predict the class. So here it will predict it is a dog, here it's going to predict that it's a cat, and here it's going to predict that it's a clownfish. Usual computer vision models architecture are the one that are often used or called convolutional neural networks, most commonly called CNN. Oops, sorry. And they are organized. I wanted to put a simple illustration of how that looks like, but basically it is several layers, one after the other one. So convolutional, pooling, convolutional, etc. And then we have another layer at the end that will flatten everything and give us our predicted class. But this is good to know. Mostly I'm not going to dig too much into this today because it is not the best way to get started in computer vision. But I think it's still important to mention those. So for example, here you can see some widely used CNN architectures or LeNet5, AlexNet, VGGNet, GoogleNet, and ResNet 50. There are also ResNet 16, different, there are a lot of different architectures for classification, but you can see on the right side of the slides here how they look like. They look like they're very complex, but they are broadly used architecture that are really easy to find with diverse Python packages. Then another model architecture that has been used more in the recent couple of years are called vision transformers. And transformers were first introduced for natural language processing tasks, so analyzing text, but then were applied to vision, so images and videos. The most famous one is VIT, Vision Transformer, but there are also some others like the Screen Transformer and the other ones I have put here on the left side. But you can see the image I put here is from the VIT paper. And it is an interesting paper to read. Transformers are really good to use, but tend to be more heavy to train and more difficult to use. So in these examples, I mostly will be using convolutional neural networks. Okay, so now that I told you what classification is, I thought it would be important to tell you how do we create that model. So first, we have what we call a training data set. So you can see here, I have all of my classes are organized, all of my images are organized per class. So I have a cluster of images of dogs, a cluster of images of cats, and a cluster of images of clownfish. So you can imagine this as being just folders, subfolders into a big folder. Then we pass them to a classification model. And it's going to train, so it's going to learn, we call that training, it's going to learn to recognize these images. And then it will be able to predict what class it is. So the first step to create this training data set is called labeling. So for example, here I have an image of a dog, and I send it to labelers, so usually human labelers. And they will say this is a dog. So this is called the label or ground truth or class. I realize it often has several names that can be confusing. So if I say label, ground truth of class, this is what I'm talking about. It's the class definition of what the image is. So then the labelers go and label all of the images. So they say cat, fish, etc. And then it creates our training data sets. And here often we will then split the dataset into train, val, and test subsets so that we can use them for the training part, then the validation part, then the testing part. Okay, so now object detection. So starting with the same images as before, now we're going to be asking the question, where are the objects on these images? So first we see that we have the cat that is here kind of like in the middle of the image. Then we have two dogs who are also in the middle, but one on the left and one on the right, and then the clownfish here. So you can see that we put a box around them, and that's what we call object detection. So here, same concept again. We give the images to the object detection CV model. It predicts bounding boxes around the objects, and it also say what class it is. So it is classification and localization. Okay, so bounding boxes coordinates are the core idea of object detection models, and there are several formats, commonly with different Python libraries, actually. So that can be something that is a bit tricky at first, but so I wanted to introduce them here. So usually you can have two corner format, center width height format, and corner size format. And you can see it just put the bounding boxes around the object, and often there are normalized coordinates, so between 0 and 1, that then you would multiply by the size of the image, so height and width of the image. If I take this example of this dog running, this is the format that I use most of the time, which is the center width height format. So basically, we know where the center of the bounding box is, Cx and Cy, center X, center Y. And then we have the height and the width of the bounding box. So then it's pretty easy to like just draw it. And this is what is going to be used in our training as well. And I'm going to explain this a bit more after I introduce some of the architectures that are often used for this task. So some of the widely used CNN architectures for object detections are RCNN, fast RCNN, faster RCNN, and YOLO, which is you only look once. And YOLO, there are 8 versions of it now. So it's been widely implemented, and that's the one that I use most of the time. Then we also have some transformers architecture that are able to perform object detection, like detection transformer, the swing transformer again here. And there is a YOLO transformer called you only look one level series. So usually those are pretty good because transformers have attention layers where they're going to really focus their attention on some specific object. But again, they tend to be slower than convolutional neural networks. Okay, so here for the labeling, similar to what I showed before, we send the images to labelers and then they label the images, but this time they draw a bounding box around the object. So here they draw the bounding box around the dog and they say this is a dog. So we have the ground truth and we have the bounding boxes coordinate with the class. Then we do that on all of the images. So you can see, even when we have 2 clownfish, for example, the bounding box is put on both of them. And then we have, so what again we call the training data set that we give to our object detection model, and it's going to learn from this. So usually the way those are organized, to give you some context, is we have a folder with all of the images, and then we have a folder with all of the coordinates of the bounding boxes, and usually they are text files with the same name as the image. So if you have image1.png in the image folder, then you will have image1.text in the label folder, and it will just have the ID of the class and then the coordinates that I showed before. So Cx, Cy, width and height of the bounding box. Great. So next really famous computer vision task is called segmentation. So starting again with our images here, the question that now we're asking is what pixels belong to the object on the images. So now we're going at a really specific level, which is pixels. So this is tasks that are used when we need a lot of precision on what we're doing, when we're detecting. So here for the cat, we would have all of these pixels belong to the class cat. For the dog here and for the clownfish, same. Usually segmentation can be used for medical imaging, a lot of the time to detect organs, tumors, or something like that, just to give you some context here too. So here again, we give our images to the segmentation model, and it predicts the pixels with the class. So there is a different type of segmentation. There is what we call instance segmentation, and there is semantic segmentation. So semantic segmentation is going to classify all pixels on an image. So that's the one on the left, where we have this blob is people, and then we have the background. And on the right, we have instance segmentation, where we have the ID of each object. So we have this blob is person 1, this blob is person 2, etc. So it's instance segmentation. So for this task, the usual computer vision CNN architecture used are UNet, which this one is really famous and has been used across many fields, but was introduced as a medical segmentation model. Then there is FCNN, SegNet, DeepLab, MaskRCNN, RefineNet, and ENet. And all of those have different advantages of flows, and it kind of depends on the project that you're working on. Some of them are larger models, so will take longer to train and longer to run live. But sometimes when you need to have really, really high accuracy, then it doesn't matter if it takes a bit longer to train. But if you need something really quick, you might need a smaller model. And then again, we have some transformer architectures that are able to perform segmentation. So here again, there is the vision transformer, the swing transformer, the transunit, mask former, max displap, and the mask transformer. And I put an example here of the transunit, which is a transformer unit model. So I thought that was interesting. Most of the time you wouldn't, also I want to emphasize here that most of the time you wouldn't have to actually write the whole architecture yourself, and you can use these models architecture that are pre-made. And there are a lot of researchers working on the best architectures possible. And so they will spend several years working on what convolutional layers do we need, or what other layers that we need. And then they will publish these results so that engineers like myself can just go and use them with real world data. So here again, the first step is to go and do labeling on our data. So here I have the image of the dog, and the labeling is drawing around the dog, and so that we create this mask. As you can imagine, this is really time consuming, so usually is more difficult task. But there are some models now that will help to automatically segment some things like that. So for example, the meta model called SAM will go and segment automatically, so that can be used to speed up some of the annotation, the labeling. So here again, we would have the labelers help with automatic tools, and they would label all of the images we have. We again split things into train, val, and test. And then here again, it's always the same pipeline. We have our trained data set, we give it to our model, it will learn. And so we train our model, it will learn and be able to perform the task. And when I say perform the task, I mean it will be able to predict the mask around each object and classify them at a pixel level. Okay. So I know I already talked a lot and I gave a lot of information, so I wanted to summarize the different notions that were introduced. So first, we have introduced a classification, which is the process of categorizing images into one of several predefined categories or classes. And actually here it can sometimes be more than one class. If we're predicting, classifying weather, for example, we can have an image and we can say it is cloudy, raining, and there is a rainbow. So it could be 3 classes. Then CNN, convolutional neural networks, which is a computer vision model architecture used for all of the computer vision tasks that we've seen. Transformers is another deep learning model architecture that was introduced originally for natural language processing, and is great because it uses self-attention mechanism, where it will focus on certain words in sentences usually, but then has been applied to computer vision where it will focus on certain patches of images. And so that makes it really, really good for computer vision tasks. Then segmentation. So this is the task where we partition an image into multiple segments, sets of pixels that belong to different classes. Then we have introduced training, which is when the model is learning from a provided labeled data sets. So then we learned about labeling, which is the action of annotating images with their ground truths to create data sets. And this work is usually done manually by labelers. Prediction is when the model is, we have a trained model that will predict what class an image belongs to, for example, for the classification case. And then object detection, which is identifying instances of objects within an image and providing a bounding box around each object. So localization and classification. Okay, so just a reminder, we've seen classification, object detection, and segmentation. So I wanted to show you how computer vision is used in industry. And something I love about computer vision is that it's used everywhere. So I tend to get bored pretty easily, for example, and that's why I chose to go into computer vision, because I can go into any field and apply my skills to a really broad range of projects. So for example, computer vision is used in several technology like self-driving cars and facial recognition systems, which are the usual famous ones. Then it's used in healthcare, so medical imaging and surgical video analysis. In climate tech, it is often used for grid optimization, biomass estimation, and habitat suitability. And then manufacturing, defect detection, grading, automation, and there are many more fields like fashion, entertainment, customer service, education, sports is a big one, and advertisement. And here I decided to show you examples from a project I've worked on so that you can then contact me and ask me questions about them. So it's not all the usage of computer vision, but some example from my career. So the first one was that I worked on pretty early in my career was automatic defect detection on number boards. So you can see it is semantic segmentation here, where the goal is to detect and localize every pixels that belong to a class. So here we're detecting nuts, shakes, the wane, and that can be used to grade number and then automate how sawmills are performing, and it's supposed to help with having better management of sawmill and less errors, and then you can track things very easily. So that was a really fun and challenging project because there are around 60 different classes of defects that you can segment on number boards, which is something I learned at the time. Then deforestation risk mapping. So this is using geospatial imagery to detect and map where the regions are most at risk of deforestation. Automatic tree diameter estimation. This one was a fun one. Basically, the user takes a picture of a tree and it will automatically detect the diameter using some binary segmentation model, tree, no tree, and then some regression model. And then my current project, which is automatic surgical instrument detection and tracking in surgical videos. Okay, so I know I've already talked a little bit about the timeline of how to train an AI model, but I wanted to really get more into the lifetime of how an AI model is trained, and it's kind of a good example of what a month of an ML engineer would look like, I guess, or a week, depends. But when you start a project in computer vision, the first thing you will do is to go and find the model architecture that you want to use. Then usually you might need to adjust the model to meet the project requirements. So here, for example, some models only take 3 channels as input. Sometimes you need more channels than this. So for example, RGB, so red, blue, green, and sometimes you need the alpha channel, for example. So might have to change the code a little bit, but that's what I mean here. Then gather and label specific field data for the project. So take a bunch of pictures of your dog and go and label them, for example. Then train the model, evaluate the model on a robust test set. Robust test set is extremely important. So what I mean by robust test set is a set of images or data with diverse example use cases that will really show how the model is performing on a wide variety of data to make sure that it's actually performing well. And then we have the model in production that will predict results on the images. So this is called inference. When the model predicts something, it's called the inference process. And then in reality, when you actually work on a project like that, you have to make sure that you can put your model into production if it meets some threshold of metrics on the test set. So for example, we need to have a model, its accuracy needs to be 98% on the test set. So then if it meets these criteria, it can go into production. The other thing is that if it's not meeting these criteria, these thresholds, we have to go back to stage 3 or 4. Mostly we would go back to 3, gather, label more data, and retrain the model. Then we have to monitor that the model in production is behaving correctly and performing well. So we have to reevaluate the model on new data all the time. So this comes from user feedback telling us the model is not performing well. For example, in the lumber scanning example, it can be the customers will tell us it's missing all of the shakes on this specific pack of images, and then they would send us the images and we would relabel them and retrain the model. It can also be automatic detection, monitoring detection pipeline where we have flags and alerts that will tell us that the performance of the model is not great, probably, and then we can go and check things. This is a field that is still in progress, and there is no stable rules around that. So it can be a bit of a tricky part here. It really depends on the project that you're working on. So as you can see here, we basically go back to stage 3 again. And then we have to evaluate the model again. So it's more of an iterative process rather than a straight linear line. And a model will always need to be worked on, and it will always get better and better, but it has to be one step at a time. And I like to say that because it's kind of the art of computer vision. It's to always go back and make it better and better and better and be able to communicate this. Great. So now the future of computer vision, as I see it from my side of the world. So I'm sure you have heard about multimodal models in the news lately, in the past year mostly. So one of them, for example, is ImageBind from Meta AI. So multimodal models are models that allow the inputs to be from different formats. So for example, we can have images and videos, but it will also take as input depth, task, heat map, some sensors, audio. So it doesn't need to be only images. It's like the realm of everything, basically. And using these multimodal images, we can do a lot of things. So that's what is called the generative models. And so usually when people talk about Gen AI, this is what it is. So it is tasks like text to image, image to image, text to video, image to video, expand an image, inputting modifiable background. So for example, here, I put the example of the runway text to image, where the user prompts, I want a picture of a small village drawn in an anime style, and then it generates that image. That could be considered computer vision because it's generating a new image. A couple of years ago, this would have been done with maybe some GANs models. So this is we're coming from text and then we create an image. So that's where the multimodality is. And then here, for example, that was an example that really surprised me at the time because I think it's great. We have the prompt that is which side of the brain is the hydrocephalus located on this image. And so basically we have text, which is the question, and then the user provides an image. So you would think in computer vision task, you would usually give the image and then have some sort of segmentation model go and segment where it is. But here with GPT-4 Vision, it is able to answer where it is. So at first it gets it wrong, and then it's correct the 2 other times. It says that it's on the right side of the brain. I'm not a doctor, but apparently it's the correct answer. The only issue you can see here is that it is not stable. So it will first give a wrong answer and then a correct answer and then a correct answer that is slightly longer than the response number two. That is a difference with traditional computer vision tasks where once a computer vision model is trained, so CNN, for example, once it's trained and you use it to run on images, so to perform inference, it will always give the same results if you run it 10 times on one image. It will always be the same. Generative AI, not really. It will always give a slightly different answer. But still, we can see that here it's performing a pretty deep level of computer vision analysis. And another one that I like is which one of this bottle of wine would be better with steak or whatever meal that you're eating. And there are several models here that were compared, so Blip2, Lava, etc., or multimodal models, and they will give recommendations. So there is also different layers of computer vision analysis here because the model was able to see on the image that there were two bottles of wines and then know that it was red and white wine and then do further analysis on that. Great. Well, this is end of part one of this talk, and you can find me on LinkedIn. If you have any question, you can also send me an email at margaux.masson21@gmail.com. And next week, I'll be digging a bit deeper into classification, object detection, and segmentation with some actual Python code, and we'll go through the evaluation process as well.
That's super interesting. I can't wait for that. And this was an amazing session as well. Thank you for sharing that with us. And a lot of people found the use cases very interesting. Um, and I can probably read out some of the questions we have. And so the first one is, do you have any recommended tutorials or projects for free resources to get started as a beginner?
Yeah, that's a great question. Actually, I have a slide for this next week in part two, where I put all of my favorite tutorials and links of tools that I use. Um, but on top of my mind right now, there are some great tutorials with libraries like PyTorch or TensorFlow, which are pretty famous tools that are used for AI in general, and they're all Python. So if you look up PyTorch tutorial, you will find them. TensorFlow tutorial is a bit easier for beginners. So that's what I would recommend, but I will have a better slides for that next week.
Awesome, thank you. The next one is there a tool for labeling?
That's a good question. I would say there are too many. And same, I have a slide for that next week of my favorite labeling tools. Most of them are not always free, but there are some that have a freemium version, so you can start for free. So the first ones that I would recommend to take a look at is called CVAT, CVAT, and RoboFlow is also one that I really like.
Thank you. The next one is, do you need to be good at math or statistics to specialize in computer vision?
Um, no, I don't think so. That's probably a controversial answer. But I think that the most important skill for computer vision is actual problem solving skills. So like really being able to go and dig into the problem and like go and fix it and be good at investigating and at being really patient as well, because you have to deal with data, you have to go and look at things visually a lot. So really patient problem solving. And I do think that being good at coding is important, which is not often something that is said, but if you know how to debug something, you're gonna not waste a lot of time. And that's often a skill that I think is missed in computer vision skill sets. So no, computer vision is not that hard and anyone can do it if you really want to do it.
Okay. I think you touched upon this a little bit, but are there pre-trained models we can use?
Yes, there are a lot of pre-trained models you can use, and I'm gonna show one next week that is one of my favorite because it's really easy to use for beginners. It's pre-trained and you can use it out of the box. So you can use it to classify images right away, for example, but you can also train it with your own images. So yes, you can find a lot of those and um, yeah, there are a lot of resources, and I'm going to also have a slide about these tools that provide open source pre-trained models.
Awesome. How do you evaluate a model?
Um, so usually you would label all of your images. Let's say we're going to do classification. You label all of your images and then you keep part of all of the label images on the side. You never show them to the model during the training, the learning phase. And you need to make sure that, for example, if I'm doing the model that I showed in the slide, so dog, cat, and clownfish, you have examples of all three of these classes in the test set, and you have enough of them, and then you go and run the train model on this test set, and you need to double check if it's matching the ground truth. So if it's predicting a dog on an image of a dog, but if it's not, for example, if it's predicting it's a cat, but it's a dog, that's incorrect and it will flag it. And I'm going to be showing some of the evaluation metrics that are usually used in computer vision next week in part 2. So just as a intro, I guess, to next week, part 2, there is accuracy, there are different scores, like the F1 score, recall, precision, and then we can use some sort of graphs to really see things visually.
That's interesting. If I were to try a classification task, how would I know how many images or labeled examples would suffice?
That's a really good question. Um, it depends of the project. If it's a really, so classification, I would say if you start with a couple hundred images, it should be enough. Something that I like to do is to start with not that many images usually. I start with a hundred, a couple hundred, and then I see if my model is behaving correctly, and then it gives me a good indicator that it's a good proof of concept, probably will work, and then I go and label more.
Um, the next one is if I want to gather some photos of cats or dogs, uh, and be able to classify a new photo, what's the process? I think you shared this a little bit, but do you just want to go over the steps once?
Yeah, sure. So if you get some images of cats and dogs, then you have to go and label them. Say it's a dog and it's a cat, and then you would use model architecture. So you call it from one of the tools that I'm going to show next week, and then you can say train on this data set, and then you can have your model. A lot of the time, what you would do actually is that there are a lot of models that are pre-trained already that you can start from. So you don't start from scratch the learning. You're going to have a model that is called pre-trained, and it's going to have some really good um, already designed, trained insights on analyzing images, and then you can build on top of that, and that's going to converge much faster.
Um, let's see. One last question. Do you have advice for a beginner that wants to learn computer vision?
Start with a project. There's like whatever you care about, like try to find if you can have some sort of computer vision application and go and train your own model and see how it's done and how it works. Next week, I'm going to show to some of there are some groups that I like who work on different computer vision or AI projects, and they have challenges and things like that. So that's also a good way to get started, is to join a group who is working on something, do your own project, or do some challenges. So like, I mean, Kaggle is the famous one, obviously, but then another one I've done in the past is a company called Ondema, and I will put a link on the slides for this one too, because they have really interesting projects that I really like, and I learned a lot with them.
Awesome. My one more question. The generative multimodal is very interesting. How can we use them?
Um, so there are different models that you can use. Lava, for example, is an open source one that you can find on GitHub and go and train yourself. I would say here that some of these models are harder to train without access to big GPUs, so big computers. But it is possible to train some of them on Google Colab. If you have the premium version, you can access the GPUs that are A100, and then you can train some of these models. It is slightly harder, but a lot of new generative models are lighter now and so more accessible. Then if you want to use, I mean, the GPT-4 Vision is with OpenAI. You can go and use this one. Be careful with confidentiality issues here. You have to go and read the policies. But I've used GPT-4 for some things and it's kind of fun. Pretty easy to use. It's an API. Yeah, I would go and look for open source models before maybe the GPT-4 so that you can really understand it.
All right. That's it on the questions. So thank you so much. Um, Thank you so much for taking the session. It was very interesting, and a lot of attendees shared the same in the chat. And we're all looking forward to next week's deeper dive uh, into computer vision.
Awesome. Well, thank you for having me. This is fun. And again, if you want to find me on LinkedIn or email, you can do it. Just tell me you were at the Women Who Code session, and I would be really happy to answer question or send more links, or even jump on a call if you want at some point.
Thank you so much. That's very kind of you. All right. Thank you everyone for joining. And we're looking forward to hosting you all again next week for part 2.
See you next week.
Thank you. Bye.